In this problem, we're being asked to construct a 95% confidence interval, and x is 28, n is 85. So I just copied the question from the homework there. So the first step is to get your sample proportion, and you should round this to 4 decimal places. Now the view and example is rounding to 4 decimal places, but the instructions say round to 3. So our final answer, I'm going to round to 3, and it worked out for this one. I'll try yours in just a second to see if it'll work out. So what I did was I have a column for x, a column for n, and a column for the population size. That way these are clearly labeled and I can just plug these into my formulas. So if you do x divided by n to get your sample proportion, x divided by n, I got 0.3294. So I rounded it to 4 decimal places. And then I highlighted it because I'm going to use this in my formula at the end. Then for the finite population correction factor, I will have to check to make sure I need this. But if you do n, your sample divided by your population, and it's greater than 0.05, you will need to use this part of the formula. And so I did n minus n and got 415, and then of course n minus 1, 500 minus 1, and that would give us 499. And the reason I use these cells to do it is if I want to work another problem, all I would have to change is x, n, and n, and it will work the entire problem for you. All right, so I did the numerator and denominator, so just take the square root of this divided by this, and I get 0.9120. For step 3, I need to calculate the standard error of the proportion. So I'm going to take C7, which is P, which is up here, right here, 0.3294, times 1 minus 0.3294, and then I would get 0.2209, and then divided by n. So I'm going to take the square root of the numerator divided by the denominator. And you want to put parentheses around the division. So you divide first and then take the square root. And I got 0.0510. Okay, and then step 4. All right, alpha divided by 2. 1 minus 0.95. And that would be 0.05. It's a 2-tailed. So we're going to divide that by 2 and get 0.025. Now I'll explain that more in another video, but just to show you what it looks like. If I have, let's see if it'll let me draw. If I have a distribution here and I want my z-score, I want way up to here, and so my z-score is going to be, this tail is 0.025, so if I say 1 minus 0.025, then the probability is 0.975. So we're kind of going backwards here. We're getting the probability and we're using that to give us the z-score. With that 0.975, you can look up the z-score because we want to use technology, and you're going to do norm.s.inverse. And let me just show you what that looks like. It's going to return the inverse of the normal cumulative distribution. So we're, like I said, we're working backwards. So we're going to click on the probability that we just found, and we're going to round this to, if I can move, I'm going to say 4, just like we've been doing. I'm going the wrong way. So it would end up being 1.96, and I'm going to erase that. Okay. Now we're ready to plug into the formula, and when we do this, what I did was I went ahead and brought it down. So I put equals and I highlighted P, which is 0.3294, so I can see it. And I did the same thing here. Okay. Then what I did was I took the z-score times the standard error of the proportion times the finite population correction factor. So that is these 3 green, the last 3 green. If you multiply those 3 together, you would get 0.091. And I'm going to go ahead and round that to 4. Okay, so now all I have to do is add for the upper. I'm going to say P plus all of this that I just multiplied. So this plus what I just multiplied. And then here I'm going to say P minus that. And I rounded my final answer to 3 decimal places just because the instructions said, it's kind of confusing because it said to round 3 decimal places as needed, but then the view and example rounds to 4. So just to be safe, I rounded to 4. And then I got 0.238 would be the lower, and then 0.421 would be the upper. Now I believe the one you were working, you should be able to plug in X, N, and N, and it should work. It should work the whole problem.